Right now, writing instructions for AI models, a process known as prompt engineering, relies heavily on human intuition. Developers guess at the right phrasing, make minor syntax tweaks, and hope the output improves, rather than building their prompts using scientific data. An existing tool called Promptfoo evaluates a prompt performance with a clear mathematical grade, but lacks the ability to fix identified problems. Conversely, Autoresearch rapidly iterates toward better answers, but operates entirely disconnected from strict evaluation metrics. Rigid evaluation and dynamic iteration exist as completely isolated philosophies. You can score your prompt or you can iterate on it, but you have to bridge the gap yourself. AutoPrompter is a system designed to integrate these two standalone functions. It merges the validation capabilities of Promptfoo with the iterative logic of Autoresearch to create a single automated workflow. Developers no longer need to deploy prompts based on human feeling. By linking evaluation directly to iteration, this system only deploys instructions that empirically win across dozens of scored tests. This visualization shows a config.yaml file. YAML is a human-readable data format used to write software configuration instructions. Through this single file, a user defines the specific task and assigns two distinct LLMs, or large language models, the Optimizer and the Target. This diagram shows the first step of the architecture. The Optimizer LLM, using a model like Gemini Qwen Flash, analyzes the task description and generates a synthetic dataset of input and output pairs to serve as a testing ground. Next, the Target LLM, such as Qwen 3.59b, runs the user's current unoptimized prompt against this newly generated test data. The system then measures the performance of the Target LLM's outputs against strict metrics, like accuracy or semantic similarity. Semantic similarity is an evaluation metric that measures how closely the meaning of two pieces of text align, even if they use entirely different words. The Optimizer LLM takes those scores, analyzes the specific failures and successes, rewrites a refined prompt, and feeds it directly back to the beginning of the cycle. By forcing two distinct models into an adversarial and cooperative loop, the system teaches itself to communicate better with other AIs without human intervention. Automated iteration hits a roadblock when models suffer from amnesia. Without a way to track history, a system will repeatedly generate and test the exact same failed prompts. This diagram shows AutoPrompter's persistent memory system, known as the ledger. It tracks the JSON data, a lightweight format for storing text, of every single experiment. When a duplicate prompt is generated, the ledger blocks it. The ledger also manages context history. It feeds the Optimizer LLM only the necessary past data, ensuring the model never exceeds its strict memory window limits while still learning from previous mistakes. Running this continuous loop via cloud APIs like OpenRouter, a service for accessing external AI models, creates a critical data risk for companies trying to optimize proprietary information. To solve this, the entire loop can run completely air-gapped. By using local servers like Llama or llama.cpp to run GGUF models, a file format specifically designed for offline AI inference, the data never leaves the local machine. Persistent memory turns basic iteration into true optimization. Pairing this with local backends ensures the loop safely processes highly classified enterprise data. AutoPrompter achieves a specific mechanical outcome. The human bottleneck has been completely removed from the prompt engineering pipeline. Manual human guessing has been replaced by rapid, autonomous scientific validation. We have to ask what kind of human engineering team sat down to architect this specific closed-loop workflow. AutoPrompter was not built by a human. It was architected, coded, and tested entirely by an account called @withNeo, a fully autonomous AI engineer. The future of software development involves humans spending less time writing instructions for machines, because machines are now autonomously building, testing, and perfecting the code for themselves.